I'd like to welcome you to the School of Earth Sciences Distinguished Lecture Series. My name is Steve Graham, Associate Dean for Academic Affairs of the school, and it's my great privilege to introduce today's guest speaker, George Hilley. George is one of our own. He did his undergraduate work here, did his PhD at Arizona State, then he did a postdoc somewhere over there on the other side of the bay, and another postdoc in Potsdam where he was the Alexander von Humboldt postdoctoral scholar. He is a superb teacher, having received the School of Earth Sciences Outstanding Educator Award, and he's also received the University Gores Award as well. He's published 60 papers in refereed journals, and today his topic is A Beautiful Hazardous Haven, the Shaping of the Santa Cruz Mountains. And this is a matter of keen personal interest to him because his house is placed perilously on top of the Santa Cruz Mountains on Skyline Drive. So, George Hilley.
Great. Well, thanks, Steve. Well, good afternoon. Let's see. Sorry, just want to coordinate my stuff. So, good afternoon. My name is George, and I'm very honored to have been asked to give this distinguished lecture. Today, I'll talk about the formation of the Santa Cruz Mountains, which form the scenic backdrop to our campus, provide recreation to our families, and as I hope you'll see, moderate our local climate. However, they're also a manifestation of the hazards that pose significant risk to our campus and the larger U.S. economy. During this talk, I hope to give you an appreciation for how this familiar landscape was formed and how the careful application of a range of traditional and state-of-the-art geoscientific tools can allow us to rationally understand, in general, the processes that produce the landscapes around us, and in particular, how the beauty that we enjoy and the hazards that we face are understandable manifestations of the steady action of Earth processes played out over millions of years. Now, before I begin, I'd like to acknowledge all that have contributed to and funded this research. I'd especially like to highlight one of our star undergraduate students, Maria Goodman's daughter. A healthy chunk of what I'll talk about today constitutes her undergraduate honors thesis and master's thesis research, and highlights our department and school's continued commitment to inspiring all of the extraordinarily talented students that we're fortunate enough to attract. Finally, I'd like to acknowledge funding from the Terman Fellowship here at Stanford, as well as a career grant from the National Science Foundation that's been instrumental in really making this research possible. So since the 1950s, the San Francisco Bay Area has successfully attracted a range of technology industries that now make it the 19th largest economy in the world if viewed as a sovereign nation. Stanford has played a key role in fueling this economy of technology, both because of excellence in research and teaching, as well as its situation in an area where natural circumstances create an exceptionally high quality of life for its inhabitants. The juxtaposition of easily developable flatlands with mountainous wilderness and a dramatic coastline affords the opportunities of professionals to work and prosper in an urban area where preserved wilderness is readily accessed. Now, one of the extraordinary aspects of the Bay Area is the dramatic microclimates that cause areas in close proximity to one another to experience qualitatively different weather. These microclimates are produced by a delicate interplay between the dominantly winter delivery of moisture from the Pacific Ocean, cold water upwelling along the coast during the summer months, the convective rise of air masses within the dry, hot portions of the central portion of California, and the interaction of airflow and moisture with the rugged topography of the Santa Cruz Mountains between the bay and ocean. In particular, the Santa Cruz Mountains form a topographic barrier that tends to moderate the effects of winter storms in the central and southern peninsular Bay Area. Those of us that live in the mountains behind campus are not surprised to learn that the amount of yearly rainfall delivered by these storms can be about up to 3 times larger than the amount of precipitation that falls in Palo Alto during the same time interval. This change in annual precipitation across the bay is coarsely correlated with changes in the locations of coastal topography. Areas where the elevations of the windward Santa Cruz Mountains are high focus precipitation on these slopes, while the leeward slopes in the bay consequently are starved of precipitation. Now, during the spring, summer, and late fall, the Santa Cruz Mountains strongly moderate daytime temperatures across the bay by controlling the dominant entry points of the marine layer into the bay area. During the summer months, heating within the inland Central Valley pulls air masses towards the inland portions of California. And during this time, the outboard deflection of the California current results in the upwelling of cold coastal waters that produce a chilled marine layer that at many times condenses fog. Airflow generated by thermal convection within the Central Valley interacts with the topography of the Santa Cruz Mountains, which tends to focus areas of penetration of the marine layer into low-lying gaps in the range. For example, the topographic low in the Golden Gate allows the cold marine layer to enter the bay, and it's this juxtaposition of bay and ocean that makes those that live in San Francisco grateful that they work at Stanford during much of the summer. Also, the marine layer sometimes cascades over the low-lying topography of the northern Santa Cruz Mountains, north of campus along I-280, or through the San Gregorio Basin as fog spills over Windy Hill. However, in these cases, the topographic buttress of the Santa Cruz Mountains affords daytime insolation the opportunity to evaporate the fog on the leeward flank of the range. During the hot summer months, moisture entering into the bay through the topographic gaps condenses overnight, producing a generally moderate climate at most times of the year. Now, the physiography of the Bay Area is the key component for producing the set of conditions that influences our daily lives in ways that we often take for granted. However, our fairly unique environment is facilitated by a fairly odd mountain range when its overall geometry is viewed objectively. This oddness arises from the fact that when viewed with a critical eye, the landscape contains at least three anomalous aspects. First, the range itself is quite elongate in the northwest-southeast direction, but is generally restricted in the northeast-southwest direction, at least along much of the peninsula. Second, while ridgeline elevations reach only about 1 kilometer above sea level, they experience this elevation drop over only the distance of about 7 kilometers in places, which produces a range that is extremely steep for its width. Third, the topography of the range changes fundamentally from these areas near San Jose and between this area and Santa Cruz, where high topography is associated with the widest portion of the mountain range. In contrast, in areas to the northwest, such as those between Stanford and Half Moon Bay, ridgeline elevations and mountain belt width systematically declines as the range narrows. The change in width and ridgeline elevations along the mountain range that is a key factor that moderates the overall delivery of precipitation to the bay and produces a generally warmer climate to the south, where ridgeline elevations are low, whereas ridgeline elevations are low in the north. Finally, this odd and skinny geometry not only shields the Peninsular Bay Area from weather, but simultaneously affords easy access to the coastal areas of San Mateo County for those that enjoy recreating along the shoreline. If one were to have to traverse a mountain range of typical aspect ratio and this width to get to the ocean, recreation may be limited and commuting to and from coastal areas might be difficult. Now, during this talk, I hope to show you that this peculiar but fortuitous topographic circumstance can be understood in a detailed way as arising from long-term Earth processes in operation in the Bay Area. Many of you have either explicitly been told or tell your students, or have been told by other geoscientists that the location of the active plate boundary corresponds to some degree to the locations of the mountains in California. And as you may know, the Santa Cruz Mountains are no exception. Indeed, all of the major mountain ranges that define the Bay Area in places correlate with the location of known active plate boundary faults. While this first-order association is fairly clear, the specific peculiarities of the Santa Cruz Mountains record a fascinating story of when and how these mountains were constructed by plate tectonic motions, and how the same sets of long-term processes that produce the physical beauty around us can also generate enormous perils to the university and world economy. Now, the association of active earthquake-generating faults within the mountains that play such a role in moderating our quality of life implies that this standard of living comes at a cost. On average, the most active of these faults, the San Andreas, has produced two Bay Area earthquakes during historic times that have resulted in widespread damage to human-built structures and loss of life. The largest of these quakes occurred in 1906 along the San Andreas Fault, which uncoincidentally traverses the Santa Cruz Mountains. This moment magnitude 7.7 to 7.9 earthquake produced extreme shaking throughout the entire Bay Area and surrounding environs, causing widespread damage to San Francisco in an ensuing fire and here on campus due to the collapse of unreinforced masonry structures. Over 80% of San Francisco was destroyed in this event, mostly due to the fires, and many structures here on campus were reduced to rubble. The length of the rupture was on the order of 300 miles and extended northward, probably to Shelter Cove near Cape Mendocino, and southward to San Juan Bautista. More recently, as many of you may personally remember, the 1989 Loma Prieta earthquake, which may have occurred on a portion of the San Andreas Fault, registered a moment magnitude of 6.9, releasing up to 30 times less energy than the 1906 event. However, even this fairly subdued event, when compared to 1906, produced about $6 billion of damage in the Bay Area, which in today's dollars is several percent of the area's GDP. Here on campus, $250 million was spent fixing the damage from the shaking. In all, the moderate magnitude and relatively distant source of the earthquake made damage from this event relatively small relative to an earthquake that might rupture the length of the San Andreas Fault in the peninsula. Despite the damage produced by this earthquake, its surface rupture was very limited or non-existent, meaning that Earth scientists would be hard-pressed to find direct datable evidence for this event if it had occurred prior to settlement and historic records. While no or little surface rupture was observed during the Loma Prieta event, areas of the Santa Cruz Mountains certainly underwent uplift, suggesting that such hidden hazards might leave an imprint in the topography of the area around the rupture. These types of hidden hazards may exist in areas where localized contraction within the crust causes rocks to be moved upward relative to sea level because of the effect of the blunting of the ruptures of these types of faults in these contractional earthquakes at moderate magnitudes. In this case, earthquakes tend to leave only a muted imprint that may be rapidly erased by geologic processes. Hence, their invisibility, or despite their invisibility, these types of events actually pose significant risk to the citizens of California. A cursory surveillance of earthquakes since 1950 shows that these types of earthquakes occur in areas where the crust is being shortened rather than horizontally translated, account for a large portion of the monetary damage to human-built structures. Many of these events were located along structures whose recent seismic activity was only poorly characterized. And so while we might be fairly blind to these events, they nonetheless pose substantial risks to lives and infrastructure. Given that such hidden events, when repeated over time, might be responsible for the construction of topography around the Bay Area, might they leave some signature in the form of the mountain range or some other measurable quantity that might help us to see where earthquakes might occur in these situations before they strike? As I'll show throughout this talk, the topography of the Santa Cruz Mountains provides an archive, albeit incomplete, of the operation of earthquake-generating faults along the peninsular Bay Area. The location of the San Andreas Fault is clearly associated with the location of these ranges, which might lead some to speculate that these mountains are uplifted simply as two plates come together. While we will see that this is certainly part of the story, such an explanation leaves many of the peculiar aspects of the range unexplained. For instance, if we view the overall topography of the mountain range in the context of the San Andreas Fault, we immediately see that down in the southeastern portion of the range, between San Jose and Santa Cruz, the high topography is systematically located on the northeastern side of the fault and abruptly and rapidly tapers to the coast southwest of the San Andreas. In contrast, in the northwestern portion of the range, between Stanford and Half Moon Bay, the topography is actually highest on the southwestern side of the fault, and elevations rapidly decrease across a topographic escarpment across the San Andreas. This transition between the side on which topography is high is fairly gradual across the range, with the topography on each side of the San Andreas more or less equivalent around the location of Los Gatos and Saratoga. Secondly, as I'll detail in a moment, the location at which crust appears to be undergoing active contraction also appears to systematically vary in the range. Again, in the area between San Jose and Santa Cruz, there's good evidence, including the 1989 Loma Prieta earthquake, that contraction and uplift are occurring, whereas areas to the northwest show that uplift is more muted. Thus, there appear to be very systematic features in the topography and deformation across the area that are not well explained by simply a uniform component of uniform contraction across the San Andreas Fault. Now, in this talk, I hope to show how these mountains might have been built over time, how we think we know this, and what this might tell us about how to evaluate the hazards posed by mountain building structures throughout coastal California. I hope to show you that a careful application of both traditional and state-of-the-art geoscience tools can provide a fairly coherent picture of the formation of this mountain range and its uplift that continues today. First, I'll provide background on the long-term interactions between the Pacific and North American plate and show how these interactions have produced the overall distribution of basins and mountains that rim the coastal areas of California. Next, I'll take a view from the surface by using traditional geologic observations that reveal when the range probably started to rise. Then I'll show how a view from the bottom up in the Santa Cruz Mountains supports these observations with modern tools that allow us to image the movement of rock through mountains towards the surface. Next, I'll take a view from the coastline to show how sea level changes in the past interact with the uplifting coastline in the Santa Cruz Mountains to archive the patterns and rates at which this range has been uplifted during the last 500,000 or so years. Finally, I'll take a view from above in which spatial patterns of erosion of the mountain of Santa Cruz basins reveal the long-term, or at least the moderately long-term patterns of uplift and erosion sustained by the range. I'll then sort of weave these observations into a somewhat internally consistent view of the mechanisms by which these mountains were uplifted and assess what the topography may actually reveal about these processes. The distribution of mountains throughout coastal California can be understood in a very coarse way in the context of plate interactions between the Pacific, North American, and now absent Farallon plates over the last 50 million years. During the Mesozoic and Paleogene, the North American and Pacific plates were not in contact, but rather the Farallon plate was translated towards North America, which caused it to subduct under the plate. However, the motion of North America relative to the Pacific plate was more or less parallel to the subduction margin, which had the effect of translating the spreading ridge separating the Pacific and Farallon plates towards the subduction zone. About 25 million years ago, the spreading ridge between these two plates encountered the subduction, which locally and instantaneously juxtaposed the Pacific plate with North America. At this instant, subduction that was facilitated by spreading began to be replaced largely by horizontal displacements where the Pacific and North American plates were now juxtaposed. This continued translation of the obliquely trending spreading center relative to the subduction margin resulted in a north and southward expansion of the juxtaposition of Pacific and North American plates over time, which progressively has replaced subduction with lateral horizontal displacement. The last vestiges of the ancient subduction zone now lie off the Pacific Northwest. The details of this process were responsible for a host of phenomena that have had a wide-ranging impact on the physiography, climate, availability of agricultural lands, and the wealth of abundant mineral and energy resources contained within our state. Although the discussion today will focus on those aspects that have produced the coast ranges, such as the Santa Cruz Mountains. During the time that the spreading ridge first encountered the subduction zone, the motion of the Pacific plate was close to parallel to the subduction zone. However, far-field rotation of the Pacific caused a component of opening to be resolved along the newly developed interface between the Pacific and North American plates. This caused localized extension along the margin, and probably as the subduction was replaced with horizontal displacement along the boundary, this conspired with some thermal weakening of the crust of North America to allow the thick crust and high topography of western North America to dilate and collapse by gravitational spreading. As a quick aside, the local dilation along the margin during this time produced a series of deep ocean basins located in close proximity to the continent. However, around 6 million years ago, a global plate reconfiguration caused a change in the direction of the Pacific plate, which resolved a small contractional component of plate motion onto the boundary. This had the effect of reversing the previous rifting, as contraction related to this convergence inverted the deep sedimentary basins and uplifted coastal mountains adjacent to the plate margin. Now, the archive of plate interactions and uplift of the Santa Cruz Mountains is in part recorded in the rocks that surround them. The range is transected by the San Andreas Fault, which accommodates part of the horizontal motion between the Pacific and North American plates. This fault currently translates outboard rocks to the northwest relative to the bay at a rate of between 15 and 20 kilometers per million years. This translation has the effect of juxtaposing rocks of substantially different origins across the fault. An additional complication within the Santa Cruz Mountains is the effect of another fault located west of the San Andreas, the San Gregorio Fault. As you can see, the current maximum extent of the coastline of the Santa Cruz Mountains is roughly limited by the location of the San Gregorio, although it does offset rocks onshore along the coast between Point Año Nuevo and San Gregorio. The rocks between the San Gregorio and San Andreas faults contain a thick succession of sediments that were deposited offshore at variable water depths, and thus their presence and continuity suggests that the Santa Cruz Mountains were uplifted above sea level sometime after their deposition. The most important of these sedimentary units is the youngest sediments deposited underwater, called the Purísima Formation, and it outcrops throughout the coastal areas and sometimes within the core of the Santa Cruz Mountains. Fossils preserved within these sediments indicate that they were deposited near sea level original, and so the age and current location of the unit provides a bound on when and how much uplift might have occurred. In places, the pile of sediment is 2 kilometers thick, and ashes within this unit indicate that it's younger than about 6.5 million years old and may be as young as about 3.5 million years old at its top, meaning that the mountains were not emergent above sea level by that time. Since that time, uplift within the mountains causes this unit to crop out at high elevations, which can be seen clearly here in this view looking from Monterey Bay towards Santa Cruz as the tan-shaded unit. Also, it's clear that in the southwestern part of the range, the elevation at which the Purissima is exposed is near sea level, however, as the core of the range is approached and the high topography is seen, this formation has been completely eroded which has the effect of exposing the underlying deeper rocks. To the north, these rocks once again are seen along the coast and the flanks of the mountains, where the thickness of this unit is up to 2 kilometers. In this area, horizontal translation causes them to actually appear in Portola Valley, where the sediments derived from initial uplift of the range are preserved on top of this formation. This juxtaposition records the activation of the modern strand of the San Andreas Fault over the peninsula over the last 3.5 million years or so. Thus, the current location of this formation indicates that the Santa Cruz Mountains were uplifted sometime after 6.5 million years ago, that uplift increases in its intensity from north to the northwest along the side of the San Andreas Fault and appears to diminish at the northwest end of the range. A slightly different picture of mountain building is painted when looking at rocks northeast of the San Andreas Fault. In particular, rocks of the Cupertino Basin here consist of greater than 600 meters thickness of detritus shed from the rocks that are now exposed in the southeastern sector of the Santa Cruz Mountains. Lava flows within the detritus indicate that these rocks were deposited starting around 3.5 to 4 million years ago. The fact that these sediments, which were deposited above sea level in rivers and alluvial fans, contain the fragments of rocks now exposed to the south requires that uplift of this portion of the range had commenced by this time. In all, the relationship suggests that the area of the current Santa Cruz Mountains were at or slightly below sea level sometime after 6.5 million years ago, after which uplift started exposing topography, at least in the southeastern sector, by about 3.5 million to 4 million years ago. Additionally, the warping of the Purissima appears to increase from the southeast to the northwest in the central portion of the range. However, after this location, the amount of warping recorded by the Purissima may diminish, at least in some parts, but nonetheless, a fairly thick section of this unit has probably been eroded from the top of this portion of the range. The fact that sediments in the Santa Cruz Mountains formed at or below sea level and have since been folded and uplifted gives us some sense of when the uplift of the mountains might have occurred. However, it's really difficult to discern how much uplift and deformation might have occurred throughout the range because it's exceedingly challenging to reconstruct the thickness of sedimentary units across the range and unfold them to estimate total deformation and uplift, although exceptional work by scientists at the USGS is currently taking on this challenging problem. Alternatively, a specific branch of geochronology called thermochronology allows us to peer into the history of uplift by determining when and how quickly rocks have approached the surface from depth. This method relies on the fact that heat transfer within the brittle crust creates a temperature gradient with depth, and these temperatures in turn affect the kinetics of transformation of Earth materials. The particular systems we have used in the Santa Cruz Mountains to determine when and how fast rocks currently at the surface approached it utilize the spontaneous decay of uranium-238, which leaves a measurable imprint in certain minerals under certain conditions. The first system that we used was the apatite fission track system. In this system, the decay of uranium-238 contained within the mineral apatite causes damage to the apatite crystal lattice in the form of a track or ellipsoidal damage zone that can be identified microscopically. At elevated temperatures, typically in excess of 125 degrees Celsius, rapid reaction kinetics cause the track to quickly heal, erasing the evidence of the decay. However, once the sample has cooled below about, at most, 60 degrees centigrade, the damage tracks created by the fission events are entombed within the crystal lattice. Because the decay rate of uranium-238 is known to first order and the temperature at which damaged tracks are retained can be estimated, this methodology can be used to date the time the rock cooled through the temperature at which damaged tracks are retained. This temperature depends on the cooling rate and composition of apatites, but a rule of thumb is that tracks are retained in apatite crystals at temperatures between about 105 to 115 degrees Celsius when the rock is cooled rapidly. With this information in hand, it's simply a matter of estimating the rate of change in temperature with depth to determine how long it took for this rock to move from this depth to the surface where it currently resides. Now, the second system that we use is apatite helium thermochronology, which exploits the spontaneous decay of uranium-238, 235, and thorium-232, which produces helium-4 during the process to reconstruct a rock's approach towards the surface. Similar to the apatite fission track thermochronology, the decay of these radiogenic isotopes in the apatite crystals embeds the helium-4 in the apatite crystal lattice. However, at temperatures exceeding about 80 degrees Celsius, the helium rapidly diffuses through the crystal lattice and is lost. However, below about 40 degrees centigrade, the helium that's embedded in the apatite crystals is retained, and thus rocks that cool through temperatures at more distant times in the past will quantitatively contain more helium than their more recently exhumed counterparts. As with the fission track system, the time at which the apatites in a rock have moved through these temperatures, once this has been determined, the depth at which this temperature was breached can be inferred by estimating the rate of change of temperature with depth. Because these two systems record a time at which a particular rock moved through different temperatures, their joint analysis allows us to track the details of how rocks may be approaching the surface as they are uplifted by mountain building and erosion removes rock from above. So previous workers, and to some extent my group, have utilized these thermochronologic methods to understand the timing and spatial patterns of building and erosion of the Santa Cruz Mountains. We know the most about the unroofing in the southern Santa Cruz Mountains using these methods, probably because this was the location of the 1989 Loma Prieta earthquake, which spurred intense interest in understanding the uplift of this area. Data published by Stanford students back in the early 1990s indicated that the high asymmetric topography on the northeast side of the San Andreas Fault near San Jose has undergone substantial uplift and unroofing, enough uplift and erosion to exhume these rocks through the apatite fission track closure temperature over the last approximately 4 million years in the highest parts of the range near Mount Loma Prieta. This suggests that the highest parts of the range had about 3 to 4 kilometers of rock removed from the surface as they were uplifted. However, the flank of this range, bordering San Jose, appears not as deeply exhumed. And in these areas, the rapid uplift observed in the core tapers somewhat and results in partial resetting of the apatite fission tracks and, in some cases, complete resetting of the apatite helium system during the last 4 or so million years. This amount of erosion is substantial and requires the mountain range to be uplifting between 0.6 to 0.8 millimeters per year during the last 4 million years. The uplift recorded by geochronology in this portion of the range appears contemporaneous with the interval during which detritus was shed from these mountains into the surrounding Cupertino Basin. Both of these lines of evidence suggest that the high peaks of this portion of the Santa Cruz Mountains were growing or had been established in the interval since 4 million years ago. In contrast, apatite fission tracks discerned from rocks across the San Andreas Fault actually tell a different story. Here, uplift and erosion of the range was insufficient to produce apatites with few fission tracks, suggesting that the thick marine sedimentary rocks in this area that are recorded in this area have experienced less erosion than their counterparts across the fault. This is consistent with the fact that portions of the Purissima Formation are still preserved at high elevations in this area. Their preservation requires that no more than the thickness of this unit, a bit less than 2 kilometers, has been removed from the surface, which agrees well with the apatite fission track analysis. And likewise, apatite helium analysis from samples in the northern exposures of where the Purissima crops out suggests that rocks near the coast in this area have not been exhumed from depths greater than 2 to 3 kilometers, which is once again consistent with the preservation of this geologic unit in this area. While we have been as of yet unable to recover samples from the center of the range, the increased deformation recorded by the removal of the Purissima suggests that sediments from the core of the range may be good candidates for having been exhumed deeply enough to expose apatites with little helium. So geologic and thermochronologic observations paint a picture of asymmetric uplift and erosion of the southern Santa Cruz Mountains, in which the high peaks in the areas outside of San Jose are associated with rapid uplift and cooling, while the lower elevation, gradually tapering areas to the southwest have had lower total uplift and exhumation. However, these measurements only provide a crude average of processes that uplift the land over several million years, and so provide a valuable but really quite incomplete picture about how the range might be uplifting in space and time. Another clue as to the processes that build the topography of the range is encoded within the interactions between land and sea that is recorded along the coastline. Many people really just don't appreciate how dynamic the coastal environment is, even over relatively short geologic time intervals, due to the substantial changes in sea level that are probably driven largely by changes in latitudinal insulation due to the wobble and changes in ellipticity in Earth's orbit over time. For instance, during the last glacial maximum, about 20,000 years ago, the expansion of the polar ice sheets reduced eustatic sea level by 117 to 130 meters below its current elevation. During this time, the San Francisco Bay was actually an inland valley, and the shoreline was approximately 30 miles outboard of where it is today. As a quick aside, we're in a period of a particularly high sea level, climate change notwithstanding. And so during much of its modern history, the bay was actually an inland valley rather than an estuary. Furthermore, the fact that the topography in the North Bay looks like it's drowning in the bay is because it is. Features such as Angel Island were inland hills that were flooded and the shoreline steepened by the incursion of the ocean into the inland valley that's now the bay. In any case, fluctuations in sea level have occurred many times during the uplift of the Santa Cruz Mountains, and the record that these events have left in the landscape and deposits are flanking the coastline. Now, the way in which coastal features are typically preserved is rooted in the observation that the action of waves upon the shoreline causes erosion of areas above the sea level and forms sea cliffs. However, as wave action erodes the land and causes the sea cliffs to migrate away from the ocean, the slope of the tidal zone is reduced, and as the cliffs are worn back. These ever-increasing ramps impart a bottom friction on the incoming waves, and thus the energy available for sea cliff erosion is generally reduced as the distance over which this drag is imparted expands. Thus, for a stable or falling sea level, sea cliff erosion may be somewhat limited by the self-defeating process. However, when sea level is rising, the nearshore water column is continuously deepening, which allows wave energy to be imparted directly to the shoreline and wave attack to continually accelerate sea cliff erosion. Following the sea level high stands, a recession of waters that occur after this point expose features that are called marine terraces because of their relatively flat geometry and cover of marine sands. The notch formed at the interface between land and ocean thus records the elevation at the sea at that time. As I had mentioned, we're currently in a particularly high period of sea level. About 125,000 years ago, sea level was probably about 7 meters higher, but in general, periods of sea level rise that fail to exceed current sea level are normally underwater. However, along actively uplifting coastlines, the continuous uplift of notches during previous high stands preserves these features well above current sea level. Thus, if we have a record of when and how large these sea level high stands might have been, we can actually use the sequence of marine terraces to determine how quickly and how constantly the land surface is being uplifted. Now, the Santa Cruz Mountains host a spectacular flight of marine terraces. They're spectacular because they can be seen with ease by eye, and their elevations systematically increase along the coast to reveal spatial changes in the rate of coastline uplift. Because each marine terrace in the set records a sea level at a particular time in the past, changes in the elevation between the different terrace levels correspond to changes in uplift rates. Finally, the chronology of these terraces really has been muddled somewhat in recent days. However, the oldest of these marine terraces is probably no older than 610,000 years, indicating that horizontal translation along the San Andreas Fault has at most translated the upper marine terrace 11 kilometers northwestward of the sea level that it recorded. These terraces are fascinating because they show a systematic increase in coastal uplift rates from effectively zero in the south to a maximum of 0.8 to 1.0 millimeters per year, after which they once again decrease again to the north. Now, in the areas around the central Monterey Bay area, there are few emergent terraces that have been identified. However, northward along the coastline, the elevation of these marine terraces increases rapidly into the town of Aptos, where they reach a maximum value in the shadow of Mount Loma Prieta. Marine terrace elevations remain high around Santa Cruz, where these features allow the wealthy residents of town to peer across the Monterey Bay on a clear day and host the UC Santa Cruz campus. The terraces are best expressed north of this area, where ranching has clearly preserved their forms. However, to the west along the coastline, terrace elevations both decrease and the distance between the recorded time horizons decreases, indicating that uplift rates are actually decreasing towards the west and north. At the northern edge of this zone, the San Gregorio Fault truncates the coastline. However, north of this zone, where the San Gregorio once again becomes submerged, coastline terraces of lesser height than at Point Año Nuevo are observed, and their elevations systematically approach sea level to the area north in Half Moon Bay. Now, tracking the relative elevation of each set of marine terraces allows us to map coastline uplift along the Santa Cruz Mountains. These coastal observations delineate a zone of rapid uplift centered in the area around Santa Cruz, where the uplift of the basal contact of the Purísima Formation is most dramatically observed. To the north and south of these areas, coastal uplift rates approach zero. However, it's interesting to point out that the uplift rates implied by the marine terraces the marine terraces around the area of Santa Cruz are on the order of 0.8 to 1.0 millimeters per year, which is really fairly similar to those to the exhumation and uplift rates recorded by the thermochronologic measurements in the corresponding areas of the landscape on the other side of the fault near San Jose. Together, these data indicate that a bullseye of uplift is occurring along both sides of the San Andreas Fault between San Jose and Santa Cruz, which is also the area that hosted the epicenter of the 1989 Loma Prieta earthquake. However, thermochronologic measurements and geologic relationships suggest that while the rates may be equivalent across the fault here, the persistence of uplift must have been much shorter on the southwestern side of the San Andreas. Otherwise, apatites would have few fission tracks, and the Purísima Formation would have been completely removed from these areas. While the current uplift rates appear somewhat symmetric across the fault, the total amount of uplift is demonstrably different. Now, the final evidence we can use to understand the details of the uplift of the Santa Cruz Mountains is to measure the abundance of cosmogenic radionuclides in samples collected from river sands. The interaction of cosmogenic radiation with Earth's atmosphere produces fast neutrons that interact with atmospheric materials and Earth's near surface. We can exploit these interactions to estimate the rates at which Earth's surface is eroded, or how long geologic materials mantling the surface may have persisted near the topographic surface. The particular interactions that we utilize involve primarily fast neutrons generated by cosmogenic radiation, and secondarily, negative muons that interact with geologic materials. As these fast neutrons interact with atmospheric target atoms, in this case oxygen, spallation of the oxygen atom produces an exotic isotope of beryllium, beryllium-10. This beryllium-10 can be mobilized in precipitation and then sequestered on the surfaces of clay minerals and soils. Because this quantity of beryllium-10 is produced throughout the atmosphere and then deposited within geologic materials, we refer to it as garden variety, or exogenous beryllium-10, since it's been imported into the surface materials. While the garden variety beryllium-10 retained in clay minerals constitutes the vast majority of this isotope found in soils, a second production path of beryllium-10 actually tends to be more useful for determining rates of erosion. In this pathway, fast neutrons generated by cosmic generation that do not directly interact with atmospheric materials reach the surface of Earth, where they can interact with the geologic materials directly. In this case, oxygen contained within the crystal lattice of the mineral quartz can be transformed into the beryllium-10, which is then locked within the crystal lattice. Because beryllium-10 is being produced directly within the materials near the surface, we commonly refer to this as in situ production. The rate of production of beryllium-10 declines with depth, since the interaction of fast neutrons with the high-density solids attenuates their flux at progressively deeper levels. A general rule of thumb is that for typical density Earth materials, the production of beryllium-10 at depths of several meters will be negligible, and this production rate increases approximately as an exponential function towards the surface. Now, as rock is moved towards the surface by erosion, it receives progressively more dosage as it traverses the upper several meters of rock. The dosage will scale with the time the rock spent within this dosage zone, and will in turn inversely vary with the erosion rate. That is, the more rapidly rocks are eroded, the shorter the exposure time, and the fewer atoms of beryllium-10 we will measure in the quartz at the surface. Now, the sands that we observe in rivers are sourced from a variety of points across the landscape that's drained by the river, and so where there's been lots of mixing, the abundance of beryllium-10 collected in river sands has been shown to provide information about the averaged erosion rate across the basin. Thus, the collection of sands from quartz-rich catchments can help us to locate hotspots of erosion, and if erosion is rapid where uplift is also rapid, it might help us to map the distribution of where active structures might be within the landscape. Now, we collected river sand samples within about 30 basins along both sides of the Santa Cruz Mountains in an effort to estimate erosion experienced by these basins over hundreds to thousands of years. Now, unfortunately, the rocks collected from the northeastern side of the San Andreas Fault did not yield material in sufficient abundance to estimate erosion rates. However, the marine sediments along the southwest side of the fault host some units that contain quartz that can be analyzed. Now, two competing constraints dictated our sampling. First, the quartz we analyzed is not contained within all geologic units in this portion of the Santa Cruz Mountains, and so the smaller areas where quartz is directly sourced from uniform lithologies was desirable. However, the river sand analysis method relies on the effect of spatial averaging to dampen the stochasticity of individual mass transport events, this effect on the erosion rates that we infer. Thus, we sampled as small basins as we could to gain high spatial resolution, while generally requiring these basins to be large enough that we might avoid dating individual mass transport events. When erosion rates were calculated from measured beryllium-10 abundance, we observed that the highest rates were nested within the southern Santa Cruz Mountains, again, where marine terrace uplift rates were highest. Erosion rates somewhat systematically decreased to the northwest along the range, mimicking the decrease in coastal uplift rates recorded in the marine terraces. Finally, when comparing the marine terrace coastal uplift rates with erosion rates, we found that there was somewhat of a correspondence between them, indicating that in a very broad sense, basins tend to erode faster when rocks within them are uplifted more rapidly. While the marine terrace and erosion rates really record two different quantities over very different space and time scales, their consistency really reinforces the idea that a hotspot of uplift may be located in the southern San Andreas Fault, right where the 1989 Loma Prieta earthquake occurred. Now, the various records of uplift within the Santa Cruz Mountains tell a somewhat puzzling tale of what creates its current topography. On one hand, long-term motions from plate reconstruction suggest that there should be some contraction and uplift across the area. While this is not resolvable in the current surface geodetic velocity field, the folding of rocks within the range, as well as the uplift of marine terraces and active erosion of basins around Half Moon Bay, suggests that two plates coming together is certainly part of the story of the uplift of this range. However, the Loma Prieta earthquake accommodated shortening across an area where marine terraces, basin-wide erosion rates, and at least northeast of the San Andreas Fault, thermochronologic data all point to the fact that the southern part of this range is likely rising faster than the range as a whole. However, the thermochronologic information also requires that while uplift of the southern Santa Cruz Mountains southwest of the San Andreas Fault is now rapid, uplift could not have persisted long without exhuming rocks from much deeper. Thus, there lies a central problem in reconciling the geologic record of uplift and deformation with that observed today. If we were to run the clock forward using the uplift rate distribution currently observed, we would not produce the topography or geologic relationships we see. Now, insight into the answer to this riddle was actually first proposed by our own Attila Eiden and later expanded on by Bob Anderson, then at UC Santa Cruz. Attila noted that currently, if one looks at the geometry of the San Andreas Fault from the north, it takes a jog to the left, which likely impacts the way in which horizontal motions are accommodated in the area. Imagine a situation in which blocks on each side of a fault are translated with respect to one another. In this case, no shortening in uplift occurs. When a component of convergence occurs between these blocks in addition to their translation, uplift may occur, but its amount may be somewhat uniform or modulated by the presence of old faults that were active in the past. However, in the event that the boundary between the two blocks deviates from their relative motion, localized rapid shortening is likely to occur in this geometric knot. Perhaps uncoincidentally, the current location of rapid uplift along both sides of the San Andreas in the southern Santa Cruz Mountains occurs within the largest of these knots along the San Andreas Fault in this portion of California. While such a knot may explain the uplift and erosion of the range over the last 500,000 years, it does not by itself provide an explanation as to the reason that uplift has persisted for the last 4 million years along the northeastern side of the San Andreas, while it could not have been sustained for this period of time along the southwestern side of the fault. However, a clue to how this might actually be reconciled may be provided by the warping of the Purísima Formation southeast of Santa Cruz. In this part of the range, recall that the base of the Purísima lies close to sea level and is progressively uplifted to the northwest. By the central Santa Cruz Mountains, this unit appears to have been completely removed before its reappearance in the northern portion of the range. Also, recall that while uplift is accruing, continued horizontal motion of material is also occurring. With these horizontal translations in mind, plate motion instantaneously produces a symmetric uplift field around the geometric irregularity. However, as horizontal motions translate material through the irregularity, uplift rates for individual rocks moving through the knot will actually change with time as they traverse its shortening and uplift field. In the case that both sides of the fault move at equal rates through the irregularity, the total uplift field and probably the consequent topography will be anti-symmetric about the bend. However, if the bend is fixed to one side of the fault, these areas that are trapped within the bend may accrue substantial amounts of uplift and unroofing through time, while areas on the opposite side of the fault will instantaneously experience similar rates, but will be moved rapidly through this uplift field over time and will not sustain the same amount of total uplift. Now, such a mechanism helps to reconcile all of these different lines of evidence into a somewhat coherent story of this uplift of the Santa Cruz Mountains and the current form of its topography. First, initial cooling of rocks in the southern Santa Cruz Mountains are consistent with the timing of deposition of sediments in the Cupertino Basin, around 3.5 to 4 million years ago. Additionally, geologic relationships in the vicinity of Montebello Ridge require that the current strand of the San Andreas Fault in back of campus actually began to accommodate the majority of plate motion during this time, although other faults that bounded subblocks within this range facilitated northwestward translation until about 1.5 million years ago. Second, it's fairly clear from the uplift of current marine terraces along the San Mateo coast that a relatively slow tapering component of uplift acts as a background engine for the construction of this range. At current rates recorded in these marine terraces, the establishment of relief and accompanying erosion in the northern portion of the range could be easily generated within this time frame. The tapering rates of coastal uplift recorded along the northern portion of the coast are commensurate with a lowering of the range, lower peak elevations, and increasing occupancy of the current landscape by the Purissima Formation, which records ancient sea level. In contrast, the slow background uplift due to convergence across the range appears to be augmented in the south, where horizontal translation of rock through a bend in the San Andreas currently enhances the uplift and erosion of the range. The highest topography of the range at Mount Loma Prieta is located where rocks appear to be trapped in this zone of rapid uplift, whereas rocks and topography on the other side of the fault show increasing elevations, warping, and level of erosion into and through the area that went through the bend in the fault. The leading edge of this area of the mountain range that was actually moved through this geometric irregularity about 3.5 million years ago actually now corresponds with the location of tapering topography within the mountain range, where none of the thick Purissima Formation is observed. These two interacting sets of processes, those that slowly uplift the range and those that localize rapid uplift within the bend in the San Andreas as materials moved into and through this knot, are at least an explanation for producing the peculiar asymmetric topography and deformation observed across the range. Thus, the overall form of the topography records a rich history that encodes the details of the processes that have uplifted the range, whose modern manifestation causes substantial hazard to this area and along the faults that actually facilitate its uplift. Now, as I hope you've seen throughout this talk, using a combination of traditional and state-of-the-art geoscience tools really can help us to reveal the processes that create the peculiarities of the topography of this range. And this is certainly enriching and helps us to understand why such disparate phenomena, such as plate motions, historic earthquakes, the form of mountains, and even the details of, or at least some of the details of the Bay Area's microclimate are actually manifestations of the slow action of processes that operate over millions of years. However, the investigations that we have performed in the Santa Cruz Mountains also lend insight into what the practical role for each of these observations might play in informing our understanding of hazards. First, one clear attribute that we noted is that rocks exposed within the range provide important constraints on the sequence and timing of events that led to its construction. However, these data do not by themselves appear to directly speak to the hidden hazards posed by the structures, such as those that produced the Loma Prieta earthquake. For example, warping of the Purissima Formation in the southern Santa Cruz Mountains may have alerted a geologist to hazards that might be related to underlying faults. However, the fact that an insufficient thickness of sediment was eroded to expose apatites with few damage tracks would leave us to wonder if warping had occurred millions of years ago or if it continued today. Likewise, the uplift recorded on the other side of the fault, in the other side of the San Andreas Fault, with these same types of measurements suggest that the faults have been really active for the last 4 or so million years, but really leaves open the question as to whether or not this activity continues today. In contrast, both the uplift of marine terraces along the coastline and the erosion rates from basins draining the mountains delineate a zone of high uplift and erosion that at least corresponds with the location of active seismicity. This makes more compelling the idea that the hidden hazards might be revealed by these types of measures. However, one can actually ask the question if there is some measure of the landscape that we can actually use to divulge information about the patterns of uplift and the rates of uplift in these types of landscapes. And this would really help us to provide reconnaissance estimates of these rates throughout landscapes. Some recent work put forth by a number of geologists that study landscapes indicate that there may be quantitative measures of the landscape form that may be used to divulge spatial variations in uplift and erosion. Given that we have a sense of what these rates might be in the Santa Cruz Mountains, we can systematically compare them to the topographic forms to determine if this might be a valuable tool for hazard assessment. Probably the most tantalizing metric that geologists have posited, based on some basic theory to correlate with uplift and erosion, is a measure of steepness of river channels that are adjusted for the systematic downstream changes in their forms. The idea is that river profiles, like the one shown here, systematically decrease their slope as watershed area increases. However, increased rates of uplift require higher channel slopes everywhere in order to evacuate the introduced rock. Thus, by adjusting our channel slope estimates for the watershed position in a landscape, we might be able to infer the broad wavelength changes in the steepness of channels that can be explained by variations in uplift. Now, within the Santa Cruz Mountains, calculation of this and other metrics show that this is not the case. While these types of metrics may be useful for deducing changes in uplift rates really across smaller and simpler landscapes, the large variations in bedrock type obfuscate the application of this metric to this particular landscape and probably many landscapes that expose rocks of different erosional resistance. Additionally, as I've hopefully persuaded you in this talk, the landscape properties represent a complex amalgam of the instantaneous uplift field that is observed today, as well as some of the integrated effects of this uplift that's revealed in the geologic record. Thus, rather than as a tool for assessing hazard, the landscape may provide a bridge for understanding the processes that produce this range that are actually recorded in the geologic record in the context of the instantaneous uplift and deformation fields that are, for instance, recorded by basin-wide erosion rates and modern-day measurements of surface motions. So, the Santa Cruz Mountains provide the scenic backdrop to our campus and play an important role in shaping our quality of life, whether it be access to mountain and coastal wilderness they provide, or the shelter from weather that we enjoy along the peninsula. Now, geologic relationships collected over the last century by geologists suggest that while some rocks of the Santa Cruz Mountains have undergone deformation for really quite some time, the widespread occurrence of deposits of the Purísima Formation, which really were deposited near sea level, suggests that much of the modern area was at sea level around the time of its deposition, sometime between 6.5 and perhaps as late as 3.5 million years ago. Uplift of the range since this time is consistent with the fact that long-term plate motions indicate that the Pacific plate started to move in a more northerly direction with respect to North America after about 6 million years ago. Thermochronologic data show that this uplift has been sustained in the southern Santa Cruz Mountains since about 4 million years ago along the northeastern side of the San Andreas Fault, but this uplift has not persisted to the southwest. Conversely, coastal uplift recorded by marine terraces and basin erosion rates highlight the fact that these areas southwest of the San Andreas are currently and have been subjected to uplift and erosion over the last at least 610,000 years that's on the order of but slightly lower than that observed than the uplift rates observed in rates on the other side of the San Andreas Fault to the northeast. This area of rapid uplift also coincides with the location of the Loma Prieta earthquake, which was hosted by an inclined structure that uplifted a portion of the range. This zone of rapid uplift is associated with a bend in the San Andreas Fault, which based on current plate motions should serve as a loci of shortening and uplift. The topography, on the other hand, appears to be an amalgam of the long-term thermochronologic record and the short-term active uplift of the range in that material southwest of the fault, of the San Andreas Fault, really appears to be moved into and then through the zone of active uplift as vertical and horizontal motions conspire with one another to limit the total uplift of this block. It's intriguing that the topography of at least the southern Santa Cruz Mountains is elongated along this side of the fault where the Purísima Formation has been completely removed by erosion, and that the leading edge of this translated uplifted material corresponds roughly with the area where ridgeline elevations begin to taper to the northwest. Thus, when viewed together, these data suggest that the steady engine of mountain building along the range is supplemented in the south by uplift of the southwestern Santa Cruz Mountains in the fault bend, which appears to have started sometime around 3.5 to 1.5 million years ago. The conspiracy of these two processes appears to create the peculiar, asymmetric, long and skinny topography of the range. Now, from the standpoint of hazard research and assessment, there are really some lessons that can be learned, I think, from the example of the Santa Cruz Mountains. First, while geologic and thermochronologic data provide an essential context for understanding the processes that really give rise to the earthquake hazards produced by these potentially hidden structures, they do not in themselves provide a reliable measure of these hazards, because changes in the rates that may accompany, for instance, horizontal translations over these long time intervals may alter or may cause the long-term geologic record to deviate from the current motions. In contrast, the uplift of marine terraces and cosmogenic radionuclide estimates of erosion rates highlighted a zone of rapid uplift and erosion that delineates the hazards that were realized in the Loma Prieta earthquake. While it may be appealing to use the topographic form as a reconnaissance tool for seismic hazard, landscape metrics appear very sensitive to the mechanical properties of the underlying bedrock, so much so as to obfuscate spatial patterns in active uplift. Nonetheless, while some of the data that we have collected within the Santa Cruz Mountains appear more important for the practical purpose of evaluating hazard, a complete view of the processes that have produced this range and ultimately create the hazard can only be gained by a unified view of mountain building using information that spans both the geologic and recent time scale, or the record from these different time scales. Thank you. Questions?
Why is the bend there, George?
Yeah, you know, I don't have a clear answer for why it's there. I always sort of just regard it as a condition of the, of the modern uplift field and topography. Simon.
What leads to the asymmetry between the two sides?
Yeah, so I think a part of that asymmetry is really due to the advection of that topography through the bend. That can't explain all of the asymmetry. One aspect that is, I think, important to consider is that when you look in the geology of that part, the southwestern block of the Santa Cruz Mountains, really as you approach the fault, you can see that the magnitude of shortening really increases quite rapidly directly adjacent to the fault. And so I think a lot of this near fault, horizontal displacement that's being accommodated over time can really localize topography near that area.
Why is the bend pinned to one side, not the other?
Yeah, oh, okay. Well, that's a different, yeah. That is a question that I leave open as an open question. Our group has been doing research on looking into the conditions that are required to actually sustain the bend and fix to one of the blocks versus the other. And the way we do this is we actually use some of these geodynamic models in order to see how the effect of different, for instance, cohesions and frictional properties of the different blocks affect how deformation is accommodated in each. We found some intriguing things that do not tell the whole story. So we can certainly produce a situation in which deformation, the location of that fault bend is actually pinned to the block that has, for instance, higher frictional and cohesive properties. However, the paradox to that we've been finding in the modeling is that when you make one side strong like that, the other deforms and can advect through, but the side that is, the side that you assign the high cohesion to actually ends up building no topography and accumulating no strain. So, I'm starting to think a little bit deeper, seeing if there's anything, any other elements that we can add to the model in order to try and understand how you can fix a bend to one side of the block while still accommodate deformation along both sides. But we're working on that, but I haven't found a good model for that quite yet. Paul.
George, from a hazards perspective, we might worry a lot about faults that bound the Santa Clara Valley and the Santa Cruz Mountains. There's really steep topography on that side of Loma Prieta. And so I'm wondering what your thoughts are about the rates of motion on those faults.
Yeah. That's down in Loma Prieta where the systems are reset, you can at least see what the long-term rates might be. I would feel, better about trying to understand what those rates might be if we had material that we could reliably date out of the erosion, out of these basins to actually determine erosion rates to see if there are these different patterns of uplift. I'd want to check back with Trevor. He counted these many, many years ago, and it's still sort of floating out there. But he counted a bunch of apatite fission tract samples across transects across the range, and some of those were actually reset along certain sets of those transects. Most notably, I believe, near Page Mill Road, there's actually some reset apatite fission tracts. I'd want to double check with him about that. But another opportunity that might exist in these areas to try and pin down what those rates might be would be to look at the deformation of fluvial terraces that are contained. There are some of these nice strath terraces, that is gravel mantled with bedrock cored terraces that have been incised into. And those, I looked to try and, the material in there is not super great for the types of analysis that would allow us to see what the ages of those different geomorphic surfaces might be. And many of them have been disturbed by, for instance, people planting orchards and stuff like that, which really makes our measurements difficult in those areas. But, in terms of actually trying to pin down what those rates would be, I think using the geomorphic toolkit, where you could actually provide some age control on some of these features that are demonstrably uplifted along these faults, would be the best way to gain that information. But so far the material hasn't been there that we can use to do that. Hi, David.
Hey, George. You carry earthquake insurance on your house? And do you have anything particular to your house to try to protect it from the next shake?
Yeah. So that was a major consideration in the purchase of the house, was how strong the foundation was and how well the house was bolted to the foundation. They actually, we saw a couple houses up there when we were shopping, some of which are like, basically they have cripple walls. Basically some of these houses are actually just sitting on what look to be almost just stone foundations. It's pretty amazing. So we were pretty careful in terms of actually doing things. We haven't had to, because we were pretty careful in the selection process in terms of actually looking to see where, looking for a house that had all the cripple walls reinforced, looking to make sure that the house was actually anchored down onto the foundation, things like this. So